Okay, good morning, everyone. Welcome back to our class from the spring break. I hope everyone stays healthy and have a good break during the weekend. Um, so I can see that we only have like 15 people in the class. Um, uh, Before we end the class, I would have a take a attendance by have a poll. So is the department's requirement to see the participation in the remote learning um, uh, mode. So yeah, right. So today we will be doing we will be starting a new chapter uh, in chapter 4. Okay, so remember, in the past we have been mostly dealing with a real value functions, meaning we are taking a values from Rn and we output a value in R, a real number. Okay, but in this case, we focus on actually vector value functions, meaning we take values in R, a real number, and we output a vector in Rn. Okay, so you can think of it as you input a time and we output the location in Rn. Okay, so for example, the projectile of an object in three-dimensional world would be considered a vector value function, right? So at a certain time, a an object would have a certain position, and the uh, the set of all this combination of time and position constitute the path of this projectile, and this would be a vector value functions, right? So when we consider the graph of these vector value functions, they are called the paths in Rn. So the projectile will be a path in Rn is it would be a curve that looks like a R1. Um, so think of it as if you have a path in Rn, right? Like this case, sorry. If you straighten out the graph of this vector value functions, it would be like a line, right? So sample. For example, in R3, okay. So maybe you have a graph looks like a helix. Okay, so Suppose this is at time 1, and this is time 2, etc., etc. And if you straighten out this path, right? This looks like a line. But is curved in R3. But if you just put it flat, here, right? So it's like a R1 object, the graph of this path. Time um, 1 and time 2. Okay, right, right. So this looks, if you recall in single variable calculus cases, if you have a function of fx, all right, and the graph of fx would be like a path here, and we can calculate the arc length, meaning if you have an endpoint here and an endpoint here, so this would be a a closed segment in R, right? Like a closed interval, so it would have a certain length. We would be interested in calculating the length of this path, meaning the total displacement of this particle when you move along this path. So in order to do that, so let me draw okay. So if this is our path, imagine this is a helix that revolves around the z-axis. Right. We're interested in finding the total displacement for this particle when it moves along the path. So we are we can approximate this um, arc length by dividing this path into certain number of segments. Okay, so for example, when this particle moves from here to here, so this is T1, so suppose this is at T0, right? And the next step, moving here, T2, again T3, T4, T5, T6, and T7, which is the endpoint. All right. So for all these segments, they are straight line connecting the starting point and the end point. Right. So for example, from T1 to T2, you go from this vector to the next vector. Okay, so the length of this segment can be calculated by the Pythagorean theorem. So, which is the length of this vector. So the length of vector here is square root of the argument in x1 and square plus the argument in x2 and then square all the way to xn. This is 1.
Sorry, I forgot what x was. Which function is x?
So the our path C is taking from R to Rn, right? So to represent this graph, right, you have n such functions, right, from x1, x2, all the way to xn. So this represents their coordinates in the range.
Thank you.
Okay. All right. So this is a general picture of approximating this arc length. Of course, this is just an approximation, right? Because you have this is just segments, and if the path is not a straight line between these 2 points, then this part is not equal to our approximation. All right, but if we take the limit as the number of segments be more and more larger and larger, right? The approximation would be more refined, and eventually it would be exactly our arc length as we desire. Okay, so let's go back. Right. So we can obtain the arc length formula. Right? The arc length is just an integration from your starting point to end point, and we are taking the integration of the x1, the derivative of x1 with regard to t, and then we square it, plus the derivative of x2 with regard to t and square, plus all the way to derivative of xn with regard to t and then square, and then we take the square root of all this sum. Okay. In order to prove the arc length formula, we need to use the mean value theorem and the single results from the single variable calculus, right? So the result is the integration can be is equal to the limit of this n sum when the number of sum is goes to infinity. Right, to put in the general picture is that x, y, and this is fx. Right? If you partition it into n parts, right, and then you would have an approximation by this rectangle. Okay, and the lemma basically says the um, uh, if the number of rectangle is larger and larger, we're taking from 10 rectangles to 100 to 1,000, all the way to infinity. All right, the sum of the area of these rectangles will be eventually equals to the area under the curve. Okay, so we can basically apply the same idea to the finding the arc length. Okay, so basically we partitioned our domain, right, A to B, starting like the starting point and end point, A and B, and then we partition it into n parts. So you have T0, T1, all the way to Tn, which is the endpoint B. Right? And each partition have equal length. Okay. Oops. Okay. All right. And then when calculating the length of this segment, right, we use the Pythagorean's theorem. So this is the length of each segment. Right. Let's go back to our graph. Oh, I think we lost it. So this is how we get the length of each segment. Okay, so we take a closer look at this part, right? X1 t ti minus x1 ti minus 1, and then square. So basically this is just the displacement in the first argument. Okay, so for each coordinate function x1, x2, all the way to xn, these functions are all real value function, right? They are taking values from R, and we output another value in R. So this is basically the same function we deal with in single variable calculus. All right, then we can apply the mean value theorem. The mean value theorem says, right? Remember, mean value theorem says FB minus FA is equal to B minus A times the derivative of F of C, where C is between A and B. So the same idea can be applied by finding some t between ti minus 1 to ti, right? We call it t1i, right? Because this is only for the first argument for x1, so I put 1 here. And I is denoted because it's between ti minus 1 and ti. So the t1i is some number between in this interval. Okay. And the length, right, the ti minus 1, because they have equal length, this is equal partition, so we can replace it by b minus a over n. Right. So this is goes to here, and you can replace all the squares, right, from x1 to x2 all the way to xn by similar treatment. So There we go. The length of the ith segment is just equal to b minus a over n times the square root of the derivative. For example, in x1, the derivative at some point between t minus 1 to ti, and then square, plus all the way to some number between ti minus 1 and ti at the derivative of xn with regard to t, and then square. All right. So when you sum up all this length of the I segment, so it becomes you just basically sum up all these square roots, right? Because they have the same factor b minus a over n here. Okay. So when you take the limit as the number of partition n goes to infinity, the the t1i, for example, remember t1i is between ti minus 1 and ti. But if the number of partition be larger and larger, the length of this partition will be smaller and smaller. And eventually T1I would be exactly Ti. Okay. Same thing for T2I, right? For x2, the T2I would converge to Ti. The same applies to, of course, all the way to the Tni, right? For xn. This number would be converging to Ti as well. Right? So the square root becomes nothing else by Ti. Right? And then we can just apply the lemma. This limit is exactly the interval from a to b. And the argument is t. All right, we are integrating over t. All right, let's see how we can apply it in some examples. Okay. So for example, if our path is from R to R3, from R to R2. So basically, this is a um, a a kind of helix in R2 when you revolve around the uh, the origin. Wait, hold on. Oh, this is just the graph of a circle that has the radius r. Sorry. Um, if the t is from 0 to 2 pi, right? So the graph start from 0, 1, and you go around a full circle and come back to 0, 1 again. All right. The length of this circle is just the arc length for the path ct from 0 to 2 pi. So when you take the derivative from 0 to 2 pi, we take the square root of the, so the x1 here is r cosine t. So the derivative of x1 with regard to t is minus r sine t. And we take the square root of it. X2 is r sine t. So x2, the derivative of x2 with regard to t is r cosine t. Okay. So when you simplify, this is r squared sine squared plus r squared cosine squared. Well, sine squared plus cosine squared is just 1. So basically, this is square root of r, a square root of r squared, which is square root of r. So the length is integration from 0 to 2 pi of r dt, which is 2 pi r. Okay. Any questions? All right. This is for, yeah,
Question.
sure.
If this is off topic, let me know. But the formula for arc length in 2 dimensions with real variables, with real valued functions, what always had a 1 in it. Where's the 1 in this case, or is it is it completely different?
So in this case, our path is our path C takes value from R, right? The argument T is a real value, and you output a vector in R2. So basically you output a position in R2. So these are points in R2, right? And you just connect all these points and becomes a path. Right?
But the formula, the arc length formula had a 1 plus the square of the derivative of in the 2-dimensional case. But there's no 1 in this case. I'm just puzzled about what happened to the 1. But maybe maybe it's irrelevant.
So you can rewrite it as, some of you might be familiar with the arc length formula for single variable cases. like this, right? In this case, you have y equals to fx. So basically this is, if you treat it as a vector value function from R to R square, basically you parameterize the graph of y by t and ft, right? The graph of this y equal to fx can be parameterized into t and ft. So in this case, let me use different. You see here, CT. Okay. Then, when you take the derivative of this argument, right? The derivative, this, C, actually this is CT. This is F, sorry. Okay. When you take the derivative with regard to T, it becomes 1 and F prime.
Okay, so it is the same. That's
Yeah,
what
so this is 1 here, 1 square, which is 1, and F prime would be just dy over dx. Okay, then you take the square. So basically this is the same thing. All right. Okay, so this is for R to R2, right? A vector value function in R2. Let's move on to some example in R3. So in this case, you have a path in R3 parameterized by cosine t, sine t, and t squared. Right? So in this case, your x1 is cosine t. So x1 prime, the derivative with regard to t, is minus sine t. Your x2 is sine t. So x2 prime is cosine t. X3 is t squared. So x3 prime is 2t. So the square root of all this derivative square is equal to the square root of sine squared t plus cosine squared t plus 4t squared. Simplify, it becomes 1 plus 4t squared. Basically, your square root of 1 plus 4t squared. And the arc length is basically the integration from the starting point 0 to the endpoint pi, square root of 1 plus 4t squared. dt. All right. Uh, well, in this case, you have to pull out a formula table that the integration of the square root of x squared plus a squared is just by the formula like this. So apply the formula, you just plug in pi here minus 0 here. So that's how you come up with the answer here, right? The evaluation of the integration is not that important. Okay. All right. Any questions? All right. Okay. All right. So as you notice, all right, if you have the vector value function path ct, right, at a certain point t, when you take the derivative with regard to t in each coordinate x1, x2, all the way to xn, you have a velocity vector. Right? Right? So basically at time t here, you have a velocity vector c prime t. So basically this tells you the direction and the magnitude of the velocity at time t, which is the rate of change in displacement, right? How far and what direction does the particle move at time t. Okay, so basically is the limit as h goes to 0, the displacement over time. So if you have the velocity multiplied by the change in time, right? This basically is the change of displacement. So basically this is the vector of the segment from time t to from t delta t. So the displacement, right? So if you have the limit as delta t goes to infinitesimally small, this will be infinitesimal displacement of particle, right? So basically, it tells you how much the particle move when the time is infinitesimally small. So we denote it as ds, right? The vector ds, by taking the derivative of x1, x2, all the way to xn, right? Because this is the displacement in the first coordinates, displacement in the second coordinates, all the way to the displacement of the nth coordinates. Okay, so we can calculate the length of all these vectors ds, right? Because the length of ds basically is the square root of the dot product of vector ds. If you remember, the dot product is basically the first argument, which is here, so x1 prime square plus x2 prime square all the way to xn prime square. Here, okay? So as you notice, the arc length is basically integration of ds. Basically, you sum up all this differential of arc length, because this is the length of displacement at t, and you move on to the next part, next time, right? T. So t1, t2, and when you're integrating along the path t, it becomes the arc length. Okay. Okay. Any questions? This idea would be important when you when we move later, we won't be able to cover it in 250, but when you go to 255 vector calculus, you will be calculating uh, line integrals or surface integrals, right? Basically, you just manipulate the ds, right, along the path. Okay. Any questions? All right. We will be taking a quick poll. Right, so I would denote some of the rest of the class time into going over some the take home projects. Okay. Um, of course, it's not the question itself, but rather just the prelude to the question. All right. So remember, the due date is at the end of the Sunday, right, at Blackboard. You upload all the way to Blackboard, and you have to show the complete work. All right. You can't just show the results without showing any work. All right. You need to show how you get it. So for the first question, uh, basically I want you to rewrite the Laplacian operator. Basically is the sum of the second order partial for x and y and z using polar coordinates, right? Using phi, rho, and theta. Right? The formula of changing coordinates is here. X is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. Right. So to do that, we reference how you can get the change of coordinate system from uh, um, Cartesian to polar coordinates. All right. So here you have x is r cosine theta and y is r sine theta. So the first step is you write um, uh, partial of r and partial of theta in terms of partial of x and partial of y by using the chain rule here, right? Partial of partial theta is partial x times partial x over partial theta plus partial y times partial y of partial theta, right? From this formula, you can get partial x of partial theta, which is minus r sine theta, and partial y of partial theta is r cosine theta. Similar things, you can do it for partial of partial r, right? So in this case, you can solve partial of partial x, right? And partial of partial y. So basically, you treat partial of partial x and partial of partial y as variable, and these are just constant, right? So you can eliminate the first variable partial of partial x when you do the algebra trick, right? Of putting r and sine theta into the other side of the equation. Right? So when you add these two, the partial of partial x is gone, right? And now you have an equation that has only partial of partial y. So again, you isolate the partial of partial y by moving this factor to the other side of the equation. So there you go, you solve the partial of partial y. And after that, you plug this in into either one of the equation, and you can solve the partial of partial x. Okay. The next step is to get the partial square of partial x squared. All right. This is basically you apply the partial x twice. Okay. But since you already have the change of coordinates for partial x, right? You can just replace this using polar coordinates, right? Theta and r here and here. Right. Remember, for this, okay, it's just partial of partial theta of minus sine theta of R over R times partial of partial theta plus partial of partial theta of cosine theta times partial R. So this is a product of a function and a partial. So when you take the partial of this product, you have to use product rule. So it's equals to, when you take the partial theta of this times partial of partial theta plus, right, minus sine theta of R times, when you have partial of partial theta applies to partial of partial theta, it becomes partial square partial theta square, right? So the recording, I will post it in my YouTube channel. I will post the link after the class. Okay. So the similar idea, you can do the product rule for this term as well. Right, I will skip this. All right.
Question?
Yeah, sure.
I think I understand from following this argument that operators are kind of sometimes being used as variables, and sometimes the operators are actually going to be operating on something. If you multiply an operator, if you add and subtract operators, you can make them disappear. But at the same time, if you put an operator before something, it turns in multiplication. Like when you distribute the operator across a expression, it actually operates. So what is it that allows us to just do algebra with these operators like they're variables? Because you couldn't do that with a multiplication sign or a plus sign as operators.
All right. So in order, the justification of this is because the operator, or the partial. This is a operator. Right? You output from a function to a function. Okay. So this is the definition of a operator. Right. So for the partial operator, right, it is linear because partial x plus partial y of a function f is equal to, let me write it down in the board. All right, so for example, for partial x, it takes a function to a function. Right. Why is the partial linear? Because if you take this operator, right, operate it on a function f, it's the same as you operate partial x first, and then you plus partial y. Right. Similarly, when you have a scalar multiplication, it's the same as you scalar multiply of the operator operated on F.
So operators are vector spaces, I guess.
Yes, but in this case, the vector is a function.
Okay, yep.
Right. So be careful is that when you have the product, right, operator on a product of a function, you have the product rule. Okay. Right. So in this case, if one of the function is another operator, for example, like this, the product rule becomes, right. First, you apply the operator on F, and you leave the other one unchanged. Plus, now you leave the F unchanged, and you apply the operator twice. Right. Why we can do that is because the operator, when you put a function, it's just another function, right? In this case, we just leave the function blank because we can basically put any function, right? This is just a space holder for another function. Make sense?
Yeah.
Right. Okay. Oops. So after all the tedious product rule and combining like terms, basically this is what you have for partial x squared, right? You can verify that yourself, and similarly you can do the same thing for partial y squared, right? So the Laplacian is just basically adding up these two second order partial, right? And then you notice some of the terms cancel out, right? You have the minus and you have the plus, so these two cancel out. Annotate. So these two terms cancel. These two terms cancel, right? And sine square plus cosine square is just 1. So basically this is 1 over r squared here. And when you add these two up together, sorry, this should be cosine square. Right, this is 1 over r. And finally, for partial of partial r square, it becomes 1. Okay, so that's how you come up with the Laplacian for the polar coordinates, right? So now a similar idea is can be applied for from Cartesian to spherical, right? First, you write down partial rho, partial phi, and partial theta using partial x, partial y, and partial z, right? This is the chain rule. Next, after you have a system of equation like this, right? In spherical, you have 3 equations, right? With 3 variables, partial x, partial y, and partial z. Now you solve partial x and partial y and partial z using partial theta, partial phi, partial row. Let me write it down. So we have partial rho, partial theta, and partial phi. Right? And the variable here is partial x, partial y, and partial z. Right? And now you just solve partial x, partial y, and partial z using these partials. And now the partial square of partial x square is just basically partial x twice. Right? Do that, right? But you have to be careful with the product rule. Same thing for y, same thing for z. And the next part is just add these three, the second order partial together, and you get the Laplacian. Right? So this is the first question.
And why were we interested in finding the Laplace, other than it was the question? What was the value of being able to
Right.
find this?
So the application for such change of coordinate system is to solve, for example, some partial partial differential equations, like the Schrodinger equation. For example, Schrodinger equation reads the Laplacian of, in this case, we use the wave function, is equals to the time independent. Hold on a second. The time independent. Oh, sorry. It reads so for example, like a Schrodinger equation, this is of course time independent, right? For a hydrogen atom. So you notice to solve this, all right, you have first you have a Laplacian, and you have the derivative of t, right? So to solve this, one of the method of solving PDE is by a method of separation of variables. So for example, in this case, the phi can be viewed as a product of your phi r theta, right? Theta is just a function of taking only variable theta. This takes only variable in rho, and this takes only variable in phi, right? corresponds to the coordinate in the in the polar in the spherical coordinate system. Okay, and this is the Laplacian in Cartesian, right? This is a partial of x squared, partial of y squared, and partial of z squared, right? So you can see that in order to apply the method of separation of variable, you have to change it into spherical coordinates, right? And the question one, right? What we did here is basically filling up the gap here. Make sense?
Yep. Right. Thank you.
Right. Let's go back. Blah, blah, blah. Right. Right. All right. The second one is Cobb-Stucker's production function with 3 inputs. In the class, we did the production function with 2 inputs. Right? And basically, now you have 3 inputs. All right. The number of the capital investment, right? Basically, could be the equipment, etc. Amount of labor, and the number of materials and supplies. Right? So now you have 3 variables, and the function reads like this. Right? In this case, the big A, alpha, beta, and gamma are constants. The variables are x and y and z. Right? Basically, it tells you how much you should invest in order to get the maximum outputs. Right? So if the capital investment, labor, and materials all have different unit costs, right? Maybe in some environment, the labor costs more. Right? In some environment, the materials and supplies cost more. And the unit cost is rho, sigma, and tau. Right? So the total number of costs is basically rho x plus sigma y plus tau z. Okay. So if you have limited amount of costs, or basically you have limited budget. Okay? Your budget is capped at M. You can't go past M. You don't have that much money. You only have at most M amount of dollars. Okay, then you want to find the maximum outputs. Basically, you want to find the maximum, absolute maximum of Q in this region. Okay. So what is the graph of this region? This region is a closed solid in R3. Let me draw a rough picture. So this is a rough solid in R3. So the boundary would be the surface around this solid. Right? And then we denote it as boundary of the solid. And inside is a closed set, U. So we divide it into 2 regions, the surface, which is the boundary, and the interior, the open set. All right. So from the for the open set U, right, you can find the critical points using by the first derivative test, and you can use the second derivative test to test whether or not the critical points are minimum, maximum, saddle point, or degenerate, right? These are local behavior, of course. We can do that because the domain here is an open set, right? And next, for the boundary term, right, the boundary basically is the level set, right? The level set where the level function is C equals to number M. Okay. And when you have the function Q with restricted to the boundary set, you will have a constrained critical point. This is the constrained critical point. And for part D, you basically use the Hessian criterion for constrained extrema, right? To test whether or not these are constraint min, constraint max, saddle point, or degenerate. Any questions?
Why is the symbol for boundary the same as the symbol for partial or differential? Is that just coincidence?
Uh, it's not a coincidence, but the reason why the mathematician use all this symbol is because they basically are the same. All right. Again, when you move on to vector calculus, right, this is a surface integral is equal to and this is the integration over inside the 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 interior of the boundary. This is called the I forgot what's the name of the theorem. Oh, Stokes theorem. All right, Stokes theorem. Yes.
So in the original boundary, the differential sign became the differential of f. So it had two meanings.
Yes, yes. All right. So this is when the partial applies to a geometric object, it means the boundary. All right. But when you have the partial applies to the f, this is called the differential form. All right. Again, you need to make sense of it later on, but this is the general idea.
Thank you.
All right. Mathematicians tends to do something like this, right? Because they just looks nice, right? You just move around the partial sign, but it's totally different meanings, right? Okay. Uh, if there's no question, then the class will dismiss.